Thank you all for your feedback in the previous session. That was great to hear. Now we're going to go right into our first keynote, which is by Jason Hickey. He leads the AI for Weather team in Google Research, which focuses on the use of machine learning to improve weather forecasting. He also has 2 degrees in computer science from Cornell University and was an assistant professor in Caltech from 1999 to 2008 before going to Google to work on their weather forecasting.
Cool.
I'm sure he's going to give us a great talk. So, Jason, when you're ready, do you want to share your screen and present?
Yes. Okay. All right. Okay, does that look good? Can you see it?
Yes, we can
Great.
see you, Jason. Thank you.
You sound clear as
Awesome.
well. Thanks.
Yeah, so I'm Jason Hickey. So I've been at Google for about 10 years now. I was academic before that. And my work for the last few years has been on using AI machine learning for weather forecasting. I'd like to talk about broadly about how we're working to use AI to address climate adaptation. And specifically, I want to focus on how we're using AI to do weather and flood forecasting. And I really have 2 messages that I'd like to be the takeaways from this. This is a slide from the Google Impact Challenge and expressing how we can use artificial intelligence to address problems in the world. And the messages that I'd like to have us take away are that we can already make a difference using AI to address global weather and humanitarian issues. And the AI technology is already mature enough to make a difference in this space. All right, and I specifically want to focus on flooding. If you look at the kinds of extreme weather events around the world, flooding affects the most people in the world. It's about twice as much as the next most extreme weather event, which is droughts, and storms are even smaller. So about 250 million people a year are affected by floods. Thousands of lives are lost due to flooding, and billions of dollars of economic damages occur due to floods. If you look in India specifically, so the upper right is an image of flooding in India. Since about 1950, the frequency of widespread extreme weather events has about tripled. So this has increased greatly due to climate change. And this is something where we'd like to step in and make a difference. And the idea here is if we can do better, higher quality flood forecasting, we can notify people and we can tell people when they need to evacuate, what the consequences of flooding are going to be. Okay, now if you dive down into that, there are really 4 steps to this. One is that we start with observations from weather satellites, stream gauges, rain gauges, radar stations, and so on. We use these to produce precipitation and stream forecasts. Then the next step is to feed those into a hydrologic model that calculates how the water flows into the rivers, what the stream levels are going to be. After that, we feed the results of that into a hydraulic model that then calculates the inundation map, where the flooding is actually going to occur. And then finally, we deliver that to people in the form of alerts. Okay, so let's go through this step by step. We are going to focus on India. So the Google Flood Forecasting Initiative is focused on the Ganges and Brahmaputra rivers. This is the colored region in the map down in the lower left part of the screen. There are radar stations. Radar is a high quality form of precipitation measurement. So there is some coverage in India. There are also weather satellites. We have standard numerical weather forecasts. And so we have lots of different kinds of data sources. And what we want to do in the first step is to do precipitation forecasting. Now, of course, weather forecasting has been around as long as there have been people around. The standard way of doing weather forecasting today is to use numerical models. And the numerical models are physics-based. They are simulations, so you simulate the atmosphere. US and the Europeans have global forecasts. So you model the entire Earth at some resolution and use that to produce forecasts that are about 1 to 10 days out. That's called medium-term forecasting, and that's shown in the green region in the middle. So these are deterministic simulations of the atmosphere that we use to calculate 10 days ahead, up to about 10 days ahead. Now beyond that, so the atmosphere is a chaotic system, and so the numerical models tend to diverge from reality around at about 10 days to 2 weeks. And so if we go beyond 2 weeks, then statistical methods will generally do better than numerical models. Also, in the short term, in less than a day or so, statistical methods can often do quite well because the numerical models are fairly predictive at that scale, but the cost of computation that usually takes between 1 and 6 hours to run a numerical model. A global model will typically take around 6 hours, 6 to 8 hours to run. And so that means if you're making predictions that are, say, 1 hour ahead, you have to have run the simulation 8 hours ago. So it's based on stale data. And so machine learning methods can actually be much more accurate in that space because we have very low latencies. So that's the idea here. So one of the when we do numerical modeling, we still want distributions of the output space. We want to calculate the probability of precipitation. So the simulations themselves are deterministic, and we have some uncertainty over the input space. So we sample the input space, we run an ensemble of predictions and use that to construct an output distribution. When we use ML, we can, in fact, instead of running an ensemble, we can calculate the output distribution directly, and that's what we're going to do in this first example. So I'm going to describe one of our models for nowcasting. This is 8-hour nowcasting precipitation predictions. The input data is based on radar. This comes from MRMS, multi-radar, multi something. I forget the acronym. So this is a multi-radar system. This is a mosaic of radars in the United States. And we're also taking the GOES satellite multispectral weather satellites. These are geosynchronous weather satellites, and also including geographical data, elevation, and forecast time as an input. So the key here is that the atmosphere is a dynamical system. And so we'll have motion, we'll have winds and evolution of storms that dynamically changing. And so the one approach that we're taking is to take a very large input region and then make a very small output predictive region in the center of that. So we take a region of 1,024 kilometers on a side as the input region, and then we make a prediction for a 64-kilometer patch in the center of that to take into account the dynamics, to allow for the dynamics. So we're doing predictions. These images that we take are radar and satellite images and geographic data at 1 kilometer resolution. Okay. The specific architecture that we're using in MetNet is to take the stack of input images, downsample the data into smaller size patches, feed those to convolutional LSTM, and apply attention to make that prediction. Hold on, okay. And in particular, we're feeding in the target time. So we make predictions from 2 minutes to 8 hours, and the target time is specified in a one-hot fashion into as one of the inputs into this model. Okay. Okay, so if we compare our results for precipitation predictions, these are at 1 kilometer resolution, a 2-minute temporal resolution. So we make a prediction for every 2 minutes. The blue line is the F1 score of MetNet. This is our machine learning architecture for this nowcasting problem. HER is a high-resolution rapid refresh. That's a numerical model that's provided by NOAA. That's the standard weather forecast. High-resolution rapid refresh means it's run very frequently at high resolution. The red and yellow lines are baseline models, so optical flow is in red, and then persistence is just where we assume that the weather doesn't change. So whatever the weather is now, we assume that that's going to be the same as the weather in the future. And as you can see, the score, the accuracy of optical, well, it's the score of persistence drops over time. The score for HER is relatively flat, and also the score for MetNet dominates the numerical model about up till 8 hours. So this is a significant result for nowcasting for this kind of machine learning. So 8 hours is a significant forecast time. Then after that point, the numerical models and the physics begin to become more accurate. Okay, this is at 1 millimeter per hour of precipitation, so a relatively low amount of precipitation. Okay, so this is what the forecast looks like. Down on the bottom, we have the ground truth from radar, and you can see the actual shape of the precipitation, high resolution precipitation. On the top, we see the distribution that's generated by the neural net. And you can see in the beginning, so in the beginning of the forecast, we retain the structure of the storms. Then over time, these probability distributions tend to spread out. So this doesn't look exactly like a normal weather forecast. Over time, that distribution will tend to blur, where the numerical forecast, because it's a simulation, a deterministic simulation, will produce something that has a high resolution structure. Yeah, high resolution structure. Okay, so this is a different kind of weather forecast. Okay, so next part for this. So going back to India, we have some coverage for radar, and the predictions that I presented so far are primarily based on radar. We take a sequence of radar images as input, and then we make a prediction for what the output precipitation is going to be. Radar is high resolution. It's about 1 kilometer resolution, about 2 minutes temporal resolution. So it's a great source of input. But when we move to other parts of the world, when we move to India, radar coverage is not complete. We don't have it everywhere. And so we'd like to have other methods for determining precipitation. So along the Ganges and Brahmaputra rivers, we don't have complete radar coverage. And so a second part to our effort is to make precipitation forecasting from other data sources besides radar. Where we have radar, we will use it, and where we don't, we want to use other sources. Okay, now one thing that is available, there are microwave satellites that measure precipitation directly. This is an image from the Global Precipitation Measurement Mission. This is a constellation of about 24 satellites, microwave satellites. They're effectively satellite radar. And each satellite, the satellites are in polar orbits. They orbit from the north to the south pole, and on each orbit, they map out a swath of about 250 kilometers wide. And so we can take multiple satellites at different positions and combine their measurements into a global map. And as you can see, this map is awesome. This is an example from last year, from October last year, and you can see exactly where the precipitation is occurring. The resolution for this is about 10 kilometers spatial and about 3 hours temporal. The reason why the temporal resolution is so low is because for any point on Earth, you have to wait till a satellite passes over that point to make a measurement. And this is about a 3-hour gap between those. And if you look at the results, the effect on hydrology, this low resolution introduces several problems. One is that there is bias, so we don't generally get so it's biased to either too high or too low a rainfall, but we also get quantitative errors where for small river basins we'll overshoot the amount of water in the river or we'll undershoot, and we also get temporal errors, shifts and when the precipitation is occurring and when the flood condition will occur. So we'd like to improve the resolution of these predictions. And our idea is we can continue to use the microwave satellites, but also include geosynchronous weather satellite data. This is high resolution, about 1 to 2 kilometer resolution data, and temporal resolution is about 10 minutes. So it's high resolution data both in space and time. The only issue is that these satellites show clouds. They do not measure precipitation directly. So this is an image from a satellite of a hurricane, and you can see the cloud structure, but you don't know from this image where exactly it's raining. So the idea is that we'll just apply machine learning to that problem. These are multispectral images. The weather satellites have multiple optical channels and multiple infrared channels. The GOES series of satellites has 16 channels, 2 in optical, 6 in near IR, and then 10 in long IR. And we'll take those, combine them with global precipitation measurement data and also elevation, climatology, and feed those into a neural net. So in this case, for the estimation problem, we're using UNets. And from that, we'll produce a precipitation estimate. This is an example of what the data looks like. On the left, we have the global precipitation measurement. So you can see it's fairly blocky. This is over Seattle. And you can see the blockiness in the spatial structure and also the temporal structure. Middle is the measurement from radar of the actual precipitation over Seattle. And then on the right is our prediction from geosynchronous satellite. And you can see we get similar kinds of spatial resolution. Of course, it's not perfect yet, but it's much higher resolution and much higher quality than what we're getting from the global precipitation measurement mission. Okay. If you look at the performance of our networks as they stand now, for low quantities of rain, so this chart shows precision recall for various rates of rain. So blue is 0.1 millimeter per hour, red is 3 millimeters per hour. For low quantities of rain, we're getting pretty good results. But as the amount of rain increases, then our accuracy decreases. This is in part due to lack of data. And of course, when we're talking about flooding in India, we really care about this heavy rain, heavy monsoon rain. And so the challenge for us is to increase our accuracy in these heavy rain cases by perhaps taking additional sources of observation or combining with numerical forecasts. Okay. All right, so the next step after this, in step 2, once we have precipitation, so we've gotten precipitation nowcasting, we have precipitation estimation from satellites. Now we take this and feed this into a hydrologic model. So on the right is a cartoon of what the problem looks like. So the blue part is a river basin. The black part is the stream network. And there are gauges along the stream. In India, this is maintained by the Central Water Commission. And these measurements are taken, say, every hour or in some cases every day. And the objective in this case is to take all of these inputs, which includes the upstream stream gauges and the precipitation into that river basin, and predict what the level is going to be 2 days ahead for the downstream gauge, the gauge at the bottom of that river basin. So if we can predict the gauge level 2 days ahead, then that will give us a 2-day warning of what possible flooding events are. So in the graph at the bottom, we see blue is the amount of precipitation, and then green is the actual stream gauge. There's a delay between precipitation and the stream gauge, and we want to make that prediction 2 days ahead. Now, the standard way to do this, the standard way to do hydrology, is to take into account all the physical processes. So this includes the amount of precipitation, where the rain fell, whether there's snow, when the snow is melting, what about evaporation, evapotranspiration, what about subsurface stream flow, and so on. There are many, many physical processes to take into account. We build a physical model and use that to predict the downstream flow. So conceptually, this is simple in a way. We just take into account all the physical processes, there are many parameters, and there are many ways that you can get this wrong. So if you get any one of these processes wrong, that will lead to errors in the output. So of course, our approach, being a machine learning team, is to bypass that whole process and use machine learning to address that problem. So we build regional models that take a river basin as input, stream gauge data as input, precipitation as input, and then we use that to predict the downstream gauge. We're taking currently about 10 years of data, training data, to train these neural networks. But if you look at the results from this, these are LSTMs. These are quality scores for classic hydrologic models. So higher quality is to the right. Okay, and so we want to have down and to the right is better. These are the classic hydrologic models, and our LSTMs are generally doing much better than any of the classic hydrologic models. And that's because, of course, they're trained on the actual data, and there are fewer sources, or yeah, it's a much simpler way to address the problem. Okay, so then we use LSTMs to do the hydrology. Then the next step after that is, given the stream levels, the gauge levels, where is the flooding going to occur? And we compute this numerically. So the challenge here is that river basins are not static. River channels are not static. So what you see on the right is typical river evolution over the period of a decade. So the river flow changes on time as the channel moves. On the left, you see a satellite image of a river channel. And so if we're calculating stream flow, the hydraulics based on old data, will get inaccurate results. And so one of the approaches that we've taken is methods that take multiple kinds of satellites, optical satellite imagery, and combine that into stereo imaging. So it is possible to pay for specialized satellites to make high quality, high resolution terrain maps. What we've done instead is, there is a large amount of satellite data that's out there, optical data, taken with different cameras at different times, and we've come up with algorithms for combining this data and performing stereographic imaging from many different kinds of heterogeneous satellites. So to do it cheaper, we make use of whatever data is out there to produce high resolution maps. We have to, of course, correct when the image was taken, what the season was when the image was taken, what the quality is, and so on. But we can combine that into high resolution maps that give us about 1 meter resolution on elevation. And so what you see on the left is an existing map using SRTM, which is a standard elevation map. On the right, we have our high resolution map that's constructed from these multiple satellites. Okay, and if you look at our flood predictions using the existing maps on the left, you see a very blurry kind of inundation map. Using the higher quality elevation data, we can get highly accurate estimates of where the inundation is going to occur. So the quality on the right is much better than it was in any existing forecast. Okay, and this is done numerically. So we build numerical models, numerical inundation models. We feed in elevation maps, and in the final step, given the precipitation that feeds the hydrology, that then feeds the hydraulics to tell where the inundation is happening, then we can produce forecasts for flooding in the river basins. Now, this is an image of an actual Google alert that went out last year in 2019 during their monsoon season. This is in cooperation with the Central Water Commission. So we make our predictions, pass that to the Central Water Commission, and then produce forecasts that we can deliver on Android devices to people in the area. So last year, we delivered about 1.5 million of these alerts in India, and the plan is this year to expand that area of coverage by about a factor of 10 within India and Bangladesh. Okay, thank you. That's my talk.
Thank you very much, Jason.
Thank you.
As someone who I share my office with a bunch of people who work on flood risk forecasting and stream channel dynamics. So that was a really great talk to hear.
Yeah, thanks.
Unfortunately, we're starting to run into time for our next keynote.
Okay.
So I'm going to pull out one question now, and then I'm sure people would love it if you could take a few minutes to engage with them in the chat. And we'll be able to follow up some in the breakout session, although we won't be able to fit everyone with questions in the same breakout room.
Okay.
So I'm going to pull out a question here from Philippe Ducau, who is asking what kinds of challenges you found when stacking ML machine learning models on top of each other, like feeding the rain prediction model into the streamflow models.
Oh yeah, so you're talking about interactions between these two. I don't have a good answer for that. So it's a concern whether the kinds of one thing that we have been pursuing is, in fact, when you take these stacked models and you're doing, it doesn't really make that much sense to stack them together. Why not just combine them into a single model? So we've been looking at combined models to do this directly, to compute the hydrology directly from geosynchronous satellite. So for exactly the reasons that you're bringing up.
Thank you. Unfortunately, we are going to have to go on to the next talk now, although I would love to have more time to ask questions.
Okay, good. Thank you.
In the chat. All right, our next talk is going to be by Dr. Lucas Joppa, who's the Chief Environmental Officer at Microsoft, where he leads the company's sustainability efforts through ongoing technology innovation, program development, policy advancement, and global operational excellence. He has a PhD in ecology from Duke University. Lucas, are you ready?
Let's do this. Let me see if I can show the screen here. Can we all see that?
Yes, we can see it, Lucas.
Perfect. Let me start my video so you can see that I, like everyone else, and Jason, are working from our home offices. So are you seeing presentation mode, or are you seeing, no, you're not.
I'm seeing your PowerPoint window with all the slides listed off the left rather than the full screen presentation. That's perfect.
Now we're seeing presentation mode, right? Perfect. Okay. Well, thanks so much. Thanks everybody for coming. Thanks for inviting me here. I am going to go against my my better nature. Well, maybe not my better nature. I'm going to go against my nature and not try to do too many or any live demos today. Usually I like to fail in person, but I've just had too many failures. I've crossed my acceptable failure rate of live demos in Zoom calls over the past couple of weeks. So, so I apologize for that. But anyway, thanks for having me in this session. I really enjoyed, Jason, your talk just before this. I think, you know, flood modeling is such a incredibly important and incredibly difficult task in this space. So I thought I would just talk a little bit, keep it pretty high level about where Microsoft's coming from on this topic, ways that we're engaging. One project that I think kind of exemplifies things, and then try to save some time for a few questions, and then see if I can also participate in the breakout session as well. So just to follow on from the introduction, I am the Chief Environmental Officer. I started and spent the majority of my career inside Microsoft Research, as I'm sure most of you know, is kind of the blue sky research arm of Microsoft, and helped lead research programs at the intersection of environmental and computer science. A few years ago, I left Microsoft Research to take a more corporate position. And for those of you who are considering following that path, maybe don't. That's what I would say. No, I'm quite enjoying myself, but I also miss the day-to-day research opportunities, and do everything I can to kind of still remain at least mildly relevant in this space. So really quickly, I just wanted to set the scene, or provide some context for where Microsoft is coming from climate change and adaptation. And really, I think the way that we think about it inside the company and the way that we talk about it publicly is that, you know, the world is facing probably the most existential challenge yet, and one of the most difficult challenges, because we have to somehow figure out how to mitigate and adapt to rapidly changing climates, which I know is the topic of this, while also sustainably feeding a human population rapidly growing to 10 billion, ensuring renewable, clean water supplies to people all over the world, and stemming an ongoing and pretty catastrophic loss of biodiversity. And you have to do all of those together. They're all inextricably linked to climate. And each of them is also inextricably linked to the overall human experience, and the growth of human economies around the world. And so you have to kind of see them as part of a holistic whole. You also have to be able to take pieces and approach them vertically to be able to try to get as much done as possible. So the way that we're thinking about this is, look, we're a platform company like many of the other cloud providers out there. We don't think that technology is the silver bullet to solving all of our climate change, and particularly adaptation and mitigation challenges. We do think that it's an underinvested in area, and we also think that you know, tech companies, that's what we do, and that's probably what we should do in this space as well, is to help provide technology solutions. So not here to say that tech's here to save the world, but I do think that if we are going to save the world, tech is going to play a role in it. And so you know, initiatives like Climate Change AI, bringing top kind of machine learning minds together to think about this, is a critical first step. And at the company, we focus on carbon, water, waste, and ecosystems as 4 kind of priority areas. And then we really look to do everything we possibly can to deploy these 5 pillars against each of those areas. So our operations, ensuring that the way that we source, manufacture, operate, and then ultimately manage products and facilities at end of life is in line with best available science. But then going beyond that and looking at innovating new products, working with customers, advocating for policies, et cetera. So that's the context, the broader corporate context that all of the work that we undertake in climate change sits within. And that's my kind of purview across the company, is to ensure that we're setting that strategy, making progress against it, and taking the best available science and advances in computer science and machine learning and bringing that in as well. And so just at a high level, to set the scene for where we are as a company on carbon and the ambitions that we have. So back in January, we reassessed where we were as a company, decided that we needed to go further and go faster. We committed to being a carbon negative company by 2030. To do that against all of our carbon emissions, our own direct carbon emissions, the carbon emissions associated with our energy consumption, which as a cloud company is not trivial. And to do that for all of the carbon emissions associated with our supply chain and our value chain, or what carbon people call scope 3 emissions. And so to take a full broad perspective of the carbon associated with our business, to ensure that we reduce our emissions by half, that we remove the rest from the atmosphere through both nature-based and technology-based solutions, and then to keep going and keep removing carbon from the atmosphere beyond our annual, any residual annual emissions, and try to go back in time and remove as much carbon from the atmosphere as Microsoft's been responsible for emitting since we were founded in 1975. And then, of course, to say, hey, a lot of this isn't possible yet. It's going to require new technologies. But even if it were, the fact is Microsoft has more resources than many organizations, and we need everything to be cheaper. And so we put in place $1 billion climate innovation fund where we'll be investing directly in carbon reduction and removal technologies. So that's kind of the carbon part of this. A couple of weeks ago, in advance of Earth Day, we doubled down on our commitment to ecosystems, to be one of the first companies to protect more land, commit to protecting more land than we use, to put our infrastructure to play by building out a dedicated system to allow people to better assess the state of the planet, to do ecosystem assessments, which are so critical for our ability to adapt and mitigate climate change issues. And then to speak out on issues like the need for national ecosystem assessments so that we can all benchmark ourselves globally on where we are. But a lot of this work, all of that ecosystem work, a lot of our carbon work even happened as the result of learnings from our program called AI for Earth, which we launched a couple of years ago now. It was a 5-year, $50 million commitment to deploying machine learning in the 4 areas of agriculture, water, biodiversity, and climate change. We started really, with nothing. We've grown that program to supporting more than 500 organizations operating in more than 80 countries around the world, and really have been using that, of course, to help and to build more scalable solutions, but also to learn about what the needs are and where the opportunities are at the intersection of environmental and computer science. We've been investing in supporting all sorts of different, machine learning projects, communities, challenges, putting our own engineering teams to work in this space, oftentimes hand or side by side with organizations that we work with across the world, and really looking for opportunities to accelerate what we know to be big challenges. And one of the projects that I just wanted to highlight as part of this work is one, sorry, I'm one slide ahead of myself. But one of the things that we realized as a result of the past kind of 2 years, and I would say it was kind of a humbling experience. It wasn't something that, I guess, it's humbling both to look back and realize, that the 2 years that you spent did some good, but also could have done much more good if you had structured things right. Also humbling to say, hey, I should have seen this kind of much earlier. And I was told this by members of the practitioners in the community as well. So, and that's really about providing kind of much more integrated core infrastructure to support the machine learning communities that are working on this, that are looking to access, of course not, gain access in some way, anyway, by hook or by crook to large environmental data sets, but also to be able to do large scale model training, and then to go beyond that and take those models and offer them up as new services to folks all around the world. I think the big learning that we have taken away from our past AI for Earth work is that we've been helping a lot of individual organizations, and I'm really proud about the work that they've done, and I'll talk about one of them in just a moment. But we haven't been really closing the most important gap of all, which is helping our community of AI for Earth grantees build on the work of each other, to make it as easy as possible for them to leverage each other's models, for them to leverage each other's code, submit new data sets, and to start to build that virtuous cycle. So that's really what we're looking to go and do next. And, you know, if there's one kind of call to action from me to this community is to get in touch with me. I don't hide myself or how to get in touch with me online, so it's pretty easy to figure that out. But also just through the AI First community about ways that we can support, ways that we can make things easier. It's really kind of the intersection of, as I said, environmental and computer science, but also research and practice that we're looking to close. And we have had a few examples of kind of glimmers, I think, of how this can work. And one that I just wanted to highlight is this small startup that we've been working with over the past year called SilviaTerra. Some of you may know of these guys, co-founded by a PhD in forestry and a PhD in computer science. I think Max and Zach. And I think that what they've been able to do, and by working with us and many other corporates, is to take their core business model, which is really about helping organizations, whether that's the timber industry or conservation nonprofits, better assess the state of the nation's forests, and to be able to say, hey, look, we're going to set a goal for ourselves to try to count every tree in the United States, which from a climate change and adaptation perspective is so important, right? Because we know that nature-based solutions, or things like carbon sequestration through tree growth, through soil sequestration, et cetera, is going to have to play a significant role in meeting our overall climate targets if we're going to have any hope of meeting 2 degree, much less, sorry, a 1.5 degree, much less a 2 degree future. So, you know, that all sounds great. We should have trees, we should plant trees, we should grow trees, we should sequester carbon with trees. When you ask, where are the trees? That's when people start kind of hemming and hawing a little bit, and the resolution of our knowledge starts to break down significantly. And so what we did with SilviaTerra was to try to help them produce a base level inventory map of trees across the United States, just that foundation of the climate adaptation pyramid that we're going to need, which is the, you know, how much is there, or what is where, how much is there, and how fast is it changing of our overall natural resources. And so, you know, I can get further details of the way that we worked with them after, but, you know, ultimately we're able to count almost 92 billion trees across the United States, which is the first time we're able to really say, hey, look, like, we're getting an you know, order approximation estimate of our nation's forest inventory. And what's really interesting about that, as kind of a corporate observer of all of this, and not just an observer, but a corporate kind of engager on this, is that we are looking to engage in markets whereby you can, whereby corporates can purchase carbon offsets. Either, you know, in our past, we purchased avoided emissions offsets. Moving forward, we're only purchasing carbon removal offsets, but nonetheless, what we need is more and more of those offsets entering the market. And that's difficult because the vast, not the vast majority, but the majority of forests in the United States, at least, are owned by small landowners, those people that own, you know, 3, 5, 10, 15 acres. And because of the, you know, the issues of overhead, bringing those sorts of assets into carbon trading markets is just cost prohibitive. And so we not only work to build this map out, but then we work to build kind of the asset trading scheme behind the scenes, and with SilviaTerra and the Nature Conservancy worked together to bring several hundred landowners as part of a proof of concept together in Pennsylvania to allow all of these just, you know, small landowners to bring their carbon assets together and to trade them back into the open markets, which then Microsoft actually purchased out of to help mature these markets. And so that's just one example where I think, you know, the way that we're looking at it is, you know, at the most boring end, you know, corporate procurement, that's great. At the most exciting end, you know, the latest breakthroughs in machine learning, those are great. But it's not until you start to bring those together in a way that actually takes research all the way into the world of practice and then procurement that real things really start to change. You know, I would put the flood initiative work that we just saw in that same category. It's, you know, taking some of the best kind of machine learning approaches that we know how to do, scaling it, you know, confronting that with reality and putting that in hands of the people that need to actually make decisions. That's kind of the task that I have in front of me every day. And, you know, it's made easier by the active participation of the research community and the active engagement of the kind of the policy and decision side of the community. And I just think that SilviaTerra is one of many examples that Microsoft has been working on over the past couple of years. Is a good example of. But anyway, I thought I would leave it there, and I think that gives me 3 minutes for questions. Is that correct? I'm not entirely sure. But.
Hi, Lucas. Thank you very much for your talk. And you're spot on about having 3 minutes for questions. Okay, perfect. Sorry. Sometimes I get done and I think I have 10 minutes and people are like, oh, you're 10 minutes over. So. Absolutely. You know, I think my favorite part of that talk was your work with SilviaTerra and the idea of counting every single tree on Earth. I love the level of precision you're going for there. Yeah, so it's pretty, I mean, just at a high level, I think this is the thing. If I would want everybody to kind of come away, you know, from today frustrated by, it's how little we actually know about Earth's natural resources, right? I mean, we've got to be the most narcissistic species on Earth, right? We spend all of our time and put all of our technology to play trying to, you know, route us to the nearest Starbucks as fast as possible, which is great when you want to go to Starbucks, but we need to realize, you know, that we really know very little about, you know, I love the work about SilviaTerra. One of my favorite part about, you know, Jason's talk, and I keep coming back to Jason's talk because that's the only one I saw. So, is how much improvement you can make just by understanding the elevation on Earth, which we don't actually understand that well. Yes. Right. There was a great Nature paper in Science or Nature paper that came out a couple months ago that drastically changed the global estimates of how many people were at risk of sea level rise through no change in climate modeling. Yep. The only thing they changed was a better estimate of how high Earth is at any particular point, right? Like that's how little we know about the planet that we live on. And that one comes up in many things that I've worked on. I've run into that. I spent a while working on gully erosion of agriculture. And changing the resolution of the topography, you could double or quadruple the amount of erosion you thought you would get in narrow streams. Yeah. And so I think... go ahead. I'm going to open you up to the chat questions in a sec. Okay, perfect. I was just going to say, look, whether it's trees, whether it's elevation, whether it's, you know, flood patterns, like one of the things I would love to see this community really kind of rally around are a core set of questions where we know that just through better classification,
we can drastically improve our knowledge about Earth's systems, right? Whether that's classification that results in better digital elevation models, whether that's classification that allows us to understand the locations of every tree in a country or on Earth. Like, just let's stop accepting, you know, that we don't know all of these things, and let's take a few areas. I don't know what, I'm not here to tell you what they are, but I do think that communities like the one represented on this call are capable of and skilled enough and powerful enough to actually take a few of those as challenge areas and say, we're just going to improve the state of the world's knowledge in these areas. I think it has the potential to be highly complementary to saying, we're just going to improve the state of the world's, you know, neural network architecture on this one problem. I think those are both valid goals, but I think that we should also be focusing on that first one that I mentioned as well.
Thank you. That's a great summary. We're running into time for the breakout rooms, but I want to get one question in. And the first one I got through this time was actually from Karthik Mukavili. Karthik, if you want to ask a quick question.
Yeah, I was wondering, hi, Lucas. So how did you manage to convince Microsoft to put aside like $50 million for this and like $1 billion? And how do you see other organizations championing such efforts? Because I would suspect it's not just Microsoft who needs to do this, but, and not only that, like you're also planning on going carbon negative, not even carbon neutral.
Yeah, well, first, I mean, it's not like we just came up with this idea out of the blue. We've been working on, we've put in place mechanisms like having an internal carbon fee, like being carbon neutral, that really we just then had to extend or expand or improve. So it wasn't like we went from 0 to 60, you know, overnight. We have been slowly accelerating. I would argue that, you know, the progress that we've been making has really just been about putting this issue in the language of that Microsoft as an organization speaks, which is, we're an engineering organization. We speak numbers and math, you know, and when you kind of break things down, the scientific community has really provided a really strong roadmap of what needs to get done. And, you know, if you leave all of the social issues and all of those things aside and just say, look, there is a carbon budget. So either you, very educated technical fellow at a world-leading company, don't believe the physics that guide the rest of your life, or you do, right? So if you do, which I'm assuming you do, then we can have a very easy conversation. And then the conversation is just, what are we going to do about it, right? And that's kind of how we approach all of these issues inside the company. We take a very science-based approach. And then, you know, the most important thing I think you said is just like, this is something everyone's going to have to do. You know, a lot of people ask us, oh, where'd the ambition come from? And I'm like, it's not ambitious. Literally what we're doing is just what everybody is going to have to do. So, you know, anybody who tries to go there as one of the early, you know, adopters is going to have to break down some of the barriers. And we're willing to do that because we have the resources that other organizations might not have. But we have got to do it in a way that allows others to follow down that same path. Because if Microsoft does it, or Microsoft and Google and Apple and Amazon do it, but nobody else does it, it's not a win for anybody, quite frankly.
Yeah.
Thank you very much, Lucas. That was a great summary there. So we're going to round out this adaptability session with 2 updates talks. And these are going to be from people who presented at previous climate change AI workshops, talking about how their work has evolved and expanded and kept growing in the time since. These talks will be introduced by PTAC.
Awesome. Thank you.
I can hear you type, by the way.
Sorry about that. So yeah, thank you so much. And I hope you guys enjoyed interacting with each other during the breakout room. The next upcoming talk, as Kelly mentioned, would be an update talk from Kolya Malkin. Kolya is a PhD student in the Department of Math at Yale University and is part of the Microsoft AI for Earth program. You heard Lucas talk about it just a short while ago. So he has presented his research at a CCAI event in the past at NeurIPS and would be providing us with an update from that work. So take it away, Kolya.
Good morning, everyone. I hope that you can see my screen.
Yes, we can.
Okay, very good. So thank you to the organizers for inviting me. I'm going to speak about our work on human-machine collaboration for land cover mapping and some updates that have taken place in the last year. Before I begin, I'd like to acknowledge this group of collaborators: Caleb Robinson, Anthony Ortiz, Blake Elias, Andy Peng, Dan Morris, Bistra Dilkina, and Nebusha Yoich. So the problem we are studying is what in computer vision is a semantic segmentation problem. Given a multi-band high-resolution aerial imagery, such as you see here, at 1 meter per pixel resolution, the aim is to label each pixel as one of several land cover classes, such as water, tree canopy, or built surfaces, as you see here. High-resolution accurate land cover maps have many applications in the conservation domain, such as for informing where to create riparian buffers to prevent erosion, monitoring changes in agricultural land use or urban development, and many other domains and industries. The semi-manual methods that until recently have been used in land cover mapping are expensive because they require a lot of human input to achieve desired accuracy. In fact, the largest high-resolution land cover map in the United States was created by the Chesapeake Conservancy for about 2% of the country's area at a cost of over $1 million over 10 months, and it's only 2% of the area. This would be very expensive at a large scale. So to optimize this process, we can train machine learning models like deep neural networks to segment imagery into the land cover classes. Unfortunately, models that are trained on imagery in one location may not work very well in another region where appearances and land types, as well as even the time of day images were taken or the type of sensors used may be different. And even more than this, around the world, there are many different stakeholders who are interested in different class definitions and have different kinds of input imagery to work with. So we need a way to take models which are trained in one region of the country or the world and fine-tune them to work in another. We want a way to do this with a minimal human labor possible. So to fine-tune a model trained in one region, such as the state of Maryland, colored in green on this map, we want to fine-tune it to work in a different region, like the part of New York shown in red on this map. We want to do this by querying humans for land cover labels in the target region in an optimal way. The typical approach to this active learning loop is to have the model pick random points, or maybe points where the model is uncertain, have humans provide new labels for these points, then retrain the model, or maybe part of the model, to fit these points, and repeat until the desired accuracy is achieved. However, in a mapping problem, we can involve humans also in the stage of querying for points. That is, users can select the points where they want to provide corrections, have the model retrained, and continue teaching it in this active learning loop. So we built this web tool that I'll show you now. So here we see the predictions of a neural net trained on imagery from America, but evaluated on imagery in Ho Chi Minh City, Vietnam. The user can click to paint the predictions over the map, and as you can see, they're not very good, because this over here is a river and not a road, as gray stands for built surface. The user can then click on points on the map of their choice to label them, such as the blue dots in the river that they've labeled as water. Then they press retrain, and the new predictions in this region become much better. The user can pan around the map and keep providing corrections and retraining. And after some time, end up with a model which makes accurate predictions on an entire large area. This was a brief demo of this tool. We performed an online study in which we asked 100 human labelers to use this tool to fine-tune models trained in Maryland to 4 areas of imagery in New York, using retraining methods that were chosen based on some offline experiments. Each user was asked to spend 15 minutes trying to reach the best performance in each area, and the model was reset in between each pair of sessions. We compared this against the models that automatically or randomly chose for which points to ask for human labels. In this work, we found that human-machine collaboration in our tool produces more accurate maps than the automatic learning setup, with labels provided for the same number of points. Additionally, we could identify users that consistently did well on the tasks, and found that each user gets better on each successive task. This is evidence of a learning loop for both the human and the machine, as the user learns which points are most useful to the machine, and the machine adapts to the new input. Our tool is now being used and tested by collaborators around the world. Now, in the second part of my talk, I'd like to give you an update on some new models we've been working on. So we are thinking about ways to take advantage of low-resolution land cover maps, which are much more widely available, to produce high-resolution land cover maps in new regions with much less human effort. For example, in the US, there is the National Land Cover Database at 30-meter resolution, which you see on the left. In 20 classes, it's updated every 10 years and is based off satellite imagery. So how can we use the coarse labels on the left and the imagery in the middle to produce the fine labels as you see on the right? One approach is with neural nets to use the low-resolution labels as a kind of weak supervision for training a deep model. This is an idea we've studied before. However, lately we've developed models using no neural nets based on what we call self-similarity. These are statistical models that model color, shape, and texture patterns in an image and can then assign such patterns to land cover labels. One such model is called the epitome, as shown here. It looks like high-resolution aerial imagery, but really it's not. This small image is a learned representation of an area of imagery 300 times as large that contains some trees, some fields, and some horizontal roads. Any little patch that you can find in this big image is likely to have a close match in the small epitome. Then we can use statistical inference algorithms on the low-resolution labels to produce a segmentation of this small epitome. Then, to classify land cover in a large image, we look at every little patch, match it to the epitomic representation, and simply copy over the labels. In addition, these models are of course very interpretable because in this small image you can see exactly what's going on. These models are showing promising results. They work well locally with much smaller amount of data. They work, in fact, better than the deep neural nets on the Chesapeake Bay land cover dataset that I showed you before. And recently, also, these methods won a large land cover mapping contest. Now, and where we're moving with these, using this and some related models, which can easily be adapted to jointly model several time points of aligned imagery at once, we're running a large project to track land cover change on the entire east coast of the United States in many more, 15 land cover classes. And we're thinking about ways to efficiently incorporate human corrections, perhaps even with many users working at once into this model. Now let me show you some results. With luck, this will work and I won't need slides. Here we are. So here we see some aerial imagery at 1 meter resolution from the year 2013. This is a suburb of Baltimore. This is what it looked like in 2017. You can see that there have been some changes both in the image quality, just this one is darker, and also some new houses have been built and others have been destroyed. The low resolution labels available here look like this. Sometimes they are inaccurate and they don't provide much information at all. Using our model, we're able to come up with the following high resolution output. Here's the image. And here are land cover predictions. Here's the 2017 image and our predictions. For example, you can see that this building in the top left has vanished, while a new neighborhood has appeared near the center of my screen. Then we've created high-resolution change maps which show which new land types have appeared in each region, and the user can pan around a map of the entire state to see the land cover changes on a large area. The predictions we get using our models, which use aligned imagery to make predictions, are much better than what we would have gotten from running models independently on imagery from 2013 and 2017, which look very different. The user can pan around the map and see predictions quickly in an entire large area. We're looking forward to many things that we can do with this tool in our large-scale land cover mapping project. To finish, I'd like to point you to this website where you can learn more about our work on land cover mapping and see some of our publications. Here's a list of a few of them. Thank you very much for your attention. Thank you again to my collaborators and to the organizers.
Thank you so much, Kolya. We are running behind schedule, so if you have any questions for Kolya, please feel free to use the chat and a future breakout room to connect with him. So now we'll move on to the next speaker. The next speaker for the day is Ankur Mahesh. He is representing ClimateAI, and Ankur is an AI engineer at ClimateAI, where he analyzes seasonal forecasts, historical observations, and long-term climate simulations with machine learning. At ClimateAI, Ankur has worked on forecasting El Nino using convolutional neural networks, and previously Ankur worked on detecting extreme weather events with deep learning at the Lawrence Berkeley National Lab. So welcome, Ankur, and take it away.
Thanks so much for that introduction. I'm here to present on forecasting El Nino with neural networks and the implications that has for agriculture. Wanted to emphasize that this is a team collaboration between ClimateAI, San Jose State University, and the Geophysical Fluid Dynamics Laboratory in Princeton. To begin, the discussion of El Nino is that it's a cycle of warm and cold temperatures in the Pacific Ocean near the equator, and it's the dominant pattern that influences seasonal climate. This means that it has tremendous implications for climate-sensitive sectors, such as agriculture, water, and energy. And the way that El Nino is measured by the climate science community is through the use of a Nino 3.4 index. The Nino 3.4 index is a rolling 3-month average of sea surface temperatures in the equatorial Pacific. Here, I've highlighted in black with a black box and red shading showing the Nino 3.4 index on a satellite image from NOAA, the National Oceanic and Atmospheric Administration. And the red shading indicates that the temperatures are abnormally warm. That means that there is an El Nino event the globe is undergoing an El Nino event at this time step. And if the temperatures were abnormally cold, the globe would be undergoing a La Nina event. Here we develop a neural network-based forecast using global temperature as the input and the Nino 3.4 index at a future date as the target. Some challenges with learning to forecast El Nino is the limited observations available to use as training data. And so the solution that we propose is to train on climate simulations. These are called atmosphere-ocean general circulation models, and they're produced by a variety of scientific organizations, such as those listed on the right. So our group at ClimateAI and another group from South Korean University at Ham et al. Train neural networks on AOGCM simulations. Our methods are largely similar in terms of the training data that we use, but two important distinctions are that we use a convolutional and recurrent neural network feeding in a time series of images, whereas they use a convolutional architecture and do convolutions in the time dimension. The second difference is that we use one input field, temperature, whereas they use two, temperature and ocean heat content. So now let's see how accurate the forecasts are. The solid red line is the observation, or the ground truth, and the blue, orange, and green lines represent the forecast from 3 different models at a lead time of 5 months. The important takeaway from this slide is that while all the models are performing reasonably well when the Nino 3.4 index is at its average state at around 0, the best model for extreme values of the Nino index is actually green, which is the CES5 dynamical forecasting model from the European Center. Some more takeaways from the accuracy of the forecast are can be seen in the plots on the right here. First, neural networks trained only on historical observations have the worst performance because of the data constraints. You can see that their correlation is consistently the lowest. Second, an ensemble of neural networks from ClimateAI and the Ham et al. Method approximately matches CES5, which is the state of the art in El Nino forecasting. But what's crucial to note is that each neural network by the 2 groups alone isn't enough to match CES5. Only the ensemble matches the performance. And finally is an evaluation of the networks at the extreme values of the Nino 3.4 index. And here, as I mentioned earlier, CES5 does perform the best, indicating that this is the next frontier for deep learning to tackle, is for very large values during a strong El Nino event and very small values for a strong La Nina event. Neural networks accuracy needs to be improved, and that's where our future research will take us. In line with today's theme on climate science and climate adaptation, we also wanted to make sure that if we provide someone with these forecasts, that these forecasts are interpretable. The beauty of working with climate data is that you can compare a neural network's saliency map, which indicates how important a certain pixel in a certain location is to the network prediction, to the influence of El Nino at that region. And that's what we've shown here in this plot, where the gray to white shading shows how important a region is for a neural network, and the purple to yellow shading shows how important El Nino is for a region. We can see that there's some agreement here, which is the network is relying on very strong El Nino regions with a strong influence of El Nino. But we also see that the network is relying on areas in the Atlantic Ocean, which don't have as much El Nino reliance as some of the other locations. This is important as we communicate neural network forecasts, and many stakeholders ask us questions like, why is your network making the predictions it is? We think that neural network visualization techniques such as saliency maps can help answer those questions and allay some of the concerns about networks being a black box. Ultimately, the goal of producing a forecast is for it to help someone. And at ClimateAI, the updates to our work have been using inputs such as El Nino forecasts, but also historical planting dates and historical weather to give people insights as to what the best decisions they can make are. For example, here, we've prepared a dashboard where some people at a location in a farm in North Dakota can use an El Nino forecast and the historical analysis to find what the ideal planting date for their season is and what the expected harvest day should be. Going forward, another important question in line with the theme of neural networks used for climate adaptation is how the predictability of El Nino will change. Right now, if we want to adapt to climate change, we have to make certain assumptions about the minimum or maximum predictability of El Nino. And so in a control scenario with no climate change, we see that El Nino is reasonably predictable, shown by the black line matching the red line in the top 2 figures. However, in a scenario of climate change, one model, the model in the left column, indicates that El Nino will be similarly predictable. But the model on the right says that there will be a massive decline in predictability. And you can see that because the black line doesn't match the red line as well. This means that there's uncertainty about the future predictability of El Nino and is something for the climate science and the machine learning communities to work on answering together. In conclusion, we think that it's useful to ground these discussions in a wide deep learning context. And deep learning offers a better computational cost at inference time. Neural networks are also more flexible because they can be trained to output just the metric of interest, not an entire three-dimensional global field. And finally, neural networks can be ensembled with other forecasts to obtain an ideal forecast, such as ensembling with another neural network architecture or with a dynamical model like CS5. If you have any further questions about the work, please feel free to contact us at ClimateAI, and we'd love to talk to you more. Thanks.
Thank you so much, Ankur. Really great presentation. So since we are running a little behind schedule, we would encourage all the participants to post questions for you in the chat as well as for Kolya. And we will move ahead with the next session. We'll take a 1-minute break and then move ahead with the next session. And one thing, just wanted to make it clear that Climate Change AI is doing some excellent work in this space, and they are a company based out of the Bay Area and is a separate entity from Climate Change AI, the organization that is organizing this this event today. So you can, in that minute, Google both of us up to learn more. So thank you so much for your patience. We will be back in about a minute. Thank you, Ankur.